The mathematical framework most commonly used to describe sequential decision-making problems is the Markov decision process. A Markov decision process, MDP for short, describes a discrete time stochastic control process, where an agent can observe the state of the problem, perform an action, and observe the effect of the action in terms of the immediate reward and of the state that is reached because of that action. An MDP is based on the Markov assumption, which can be formulated as the future is independent of the past given the present. A consequence of the Markov assumption is that in order to make the optimal decision, we can simply rely on the observation of the current state, without the need of remembering how we reached it. For instance, when we play with the Rubik's Cube, it is useless to know how we have reached the current configuration of the cube in order to solve it. This implies that we do not need to keep in memory the history of the interaction between the agent and the environment, thus greatly simplifying the problem. A discrete time finite MDP is composed of a finite set S of states, a finite set A of action, a state transition function P. In particular, P of SA S prime is the probability of reaching state S prime when we perform action A in state S. A reward function R, so that R of SA specifies the immediate reward associated to the execution of action A in state S. A discount factor gamma, which specifies the importance of future rewards compared to the immediate rewards. To define the behavior of an agent, we use the concept of policy. A Markovian policy is a function that specifies for each state what is the probability of executing the different actions. If in any state the policy gives all the probability to a single action, we say that the policy is deterministic. Otherwise, the policy is stochastic. Solving an MDP means finding the optimal policy, which is the policy that maximizes some cumulative function of the reward. The most common objective function is the expected discounted sum of future rewards. In the summation, the reward at time I is multiplied by the discount factor raised to the power of I minus 1. The value of the discount factor, which needs to be in the range 0, 1, specifies how much future rewards are relevant for the agent. If the discount factor is equal to 0, it means that the agent is only interested in maximizing the immediate reward, while a discount factor equal to 1 means that the agent gives the same importance to all the rewards, independently of when they will be collected. In general, low values of the discount factor will induce myopic behaviors, while high values will generate far-sighted policies. In order to understand how to compute the optimal policies for an MDP, we need to introduce the concept of value function. Given a policy pi, its value function v pi is a function that for each state S specifies the expected discounted reward that can be obtained starting from state S and following the policy pi. The value of a state S using policy pi can be expressed by a recursive equation known as Bellman expectation equation. According to this equation, the value of a state S can be expressed as the expected immediate reward that policy pi can get from this state, plus the discounted expected value of the state that is reached after one step. Considering the Bellman expectation equations for all the states in the MDP, we get a system of linear equations, where the number of equations and the number of unknowns are both equal to the number of states. Under the assumption that the discount factor is less than 1, the value function of any policy pi can be obtained by solving the system of Bellman equation in closed form. In order to solve an MDP, we need to find a policy that achieves the maximum value possible in any state. It can be proved that for any MDP, it always exists at least one deterministic Markovian policy that is optimal. Furthermore, all the optimal policies have the same value function, called optimal value function, whose values are optimal in any state. As done for the value function of a policy, we can write a recursive equation also for the optimal value function. using the so-called Bellman optimality equation. We can see that in this equation, the expected value over the action presented in the Bellman expectation equation has been replaced by a maximization over the actions. Unfortunately, this small change has a significant impact, as the equations are no longer linear in the unknowns. Therefore, no closed-form solution exists. However, it is possible to solve MDPs using iterative approaches. The most used ones are two dynamic programming algorithms, value iteration and policy iteration. In value iteration, we start from an arbitrary value function and, iteratively, we apply the right-hand side of the Bellman optimality equation to the value function output in the previous iteration. In this way, we produce a sequence of value functions that has the property of converging to the optimal value function. In policy iteration, we start from an arbitrary policy, and then we iterate over two steps, policy evaluation and policy improvement. In the policy evaluation step, we compute the value function of the given policy pi, while in the policy improvement step, we compute the so-called greedy policy pi prime, which is the policy that maximizes the utility estimated from the value function of policy pi. It can be proved that policy pi prime is never worse than policy pi in any state. When, during the iteration, we find a policy pi prime that has the same value function of policy pi, it means that we have found the optimal value function, and that pi and pi prime are optimal policies. Dynamic programming algorithms allow us to solve MDPs when the state transition model and the reward function are known. When one or both of these elements are unknown, we need to resort to reinforcement learning algorithms, which will be overviewed in the next lesson.